We deploy some incredibly aggressive tactics to keep our environments clean. We hose down streets, wipe down counters, and flood hospital wards with chemical bleach. But the moment that chemical evaporates, the surface is entirely defenseless again. This vulnerability is exactly what drives the rise of multi-drug-resistant bacteria, strains that survive traditional antibiotics and serve as the primary cause of hospital-acquired infections. Give these resilient pathogens just a few minutes on a freshly sterilized hospital floor, and they will rapidly divide, completely reclaiming the territory. Fighting a microscopic enemy with mops and spray bottles is a losing battle. To change the outcome, human infrastructure must be engineered to clean itself. The scientific community has identified an ideal weapon for this job: silver nanoparticles. When these microscopic shards of silver encounter a pathogen, they physically shred the bacterial membrane, flood the interior, and disrupt the organism's DNA so it cannot replicate. Because this is a brutal physical destruction, bacteria cannot build a biological defense against it. Researchers wanted to take this silver and embed it directly into ceramic tiles, the exact material we use to line hospital corridors and commercial kitchens. But there is a massive engineering hurdle. To make a standard ceramic tile, you have to bake it in a kiln at over 1200 degrees Celsius, an environment that incinerates most additives. The technical challenge is clear. The silver nanoparticles must be integrated into the ceramic without vaporizing their pathogen-killing power in the kiln. Researchers established a side-by-side comparison of two application methods. Method A involved mixing a water-based silver solution into the glaze before the primary bake. This meant the tile and the silver nanoparticles were locked inside a kiln at 1225 degrees Celsius for nearly an hour. It resulted in a complete failure. The finished surface had almost no antibacterial power. Microscopic analysis explains why. When we look at a cross-section of the treated tile, we see a rough, highly porous internal structure beneath the top glaze. X-ray scanning revealed that under the extreme heat, the silver liquefied and diffused deep into these useless, porous internal layers. The silver survived the kiln, but it was lost to the depths of the tile. Because the heat sank the active agent, the top glaze was left entirely defenseless against pathogens. This led to Method B. Instead of water, scientists mixed the silver with chemical solvents and applied it only after the tile had already survived the main bake. This post-firing application required only a third fire, a much gentler bake at 600 degrees for just a few minutes. Electron microscopy proved this was the solution. On this test sample, tile 13S, the metallic silver crusters remained exactly where they needed to be, sitting securely on top of the glaze. This chart shows the biological results over a 24-hour period. When exposed to 4 major hospital pathogens, including E. coli and Staph, the bacteria populations plummeted, resulting in a 99% reduction. But the researchers uncovered a second factor in the tile's performance. The physical shape of the tile is just as important as the chemicals coating it. It comes down to surface topography. A smoother glaze physically repels bacteria, denying them the microscopic footholds and crevices they need to attach and multiply. True antibacterial power requires a two-front defense. It requires low-heat chemistry to preserve the silver, and an ultra-smooth physical surface to deny the enemy a landing zone. We have spent centuries treating hospital wards as vulnerable spaces where infections inevitably spread from bed to bed. This research points to a reality where the room itself fights the infection. However, this efficacy depends on manufacturing data. Many consumer products use the antibacterial label without the scientific backing to confirm long-term survival of the active agents. As this study proves, adding the right chemical is only the first step. If the manufacturing temperature and timing aren't precisely controlled, the biological function is destroyed before the product leaves the factory. The future of infrastructure depends on these manufacturing nuances. Walls, floors, and counters can be inherently weaponized at the microscopic level. By controlling the heat-driven diffusion of silver within a glaze, we can convert passive building materials into active defense.